All right, so now that we've talked a lot about eigenvalues, we're gonna now begin talking about eigenvectors. Okay, so again, let's recall the setup. You have an n by n matrix A, and nothing. And the definition is that a scalar lambda is an eigenvalue of A if there exists x not equal to 0 in Rn, such not necessarily Rn, exists x not n-dimensional vector in x not equal to 0, such that Ax is lambda x. Okay. And this equation is the key, and such x, such x not equal to 0 again is an eigenvector of A with eigenvalue lambda. Okay. Okay, so in other words, eigenvectors of A with eigenvalue lambda are non-zero solutions to this equation, A minus lambda I x, A minus lambda I times x equal to 0. Okay. And we've given names to these things before, right? But we know that O solutions to A minus lambda I x equals to 0 form a subspace, right? Now the definition is the following: the null space or kernel of A minus lambda I is called the eigenspace of lambda. Okay, so the collection, in other words, the collection of eigenvalue vectors with eigenvalue lambda forms a subspace, and that's called the eigenspace of lambda. Okay, the dimension of this eigenspace of lambda is called geometric multiplicity of lambda. Okay, geometric multiplicity is the dimension of the eigenspace. Now, recall that there's another notion of multiplicity, the algebraic multiplicity. Lambda is the number of times lambda occurs in the characteristic polynomial in the roots of the characteristic polynomial. In the roots of the characteristic polynomial, which is the determinant of A minus Ti. Okay, so there was the notion of algebraic multiplicity that we defined for eigenvalue lambda. And now we define the geometric multiplicity of the eigenvalue lambda to be the dimension of its eigenspace. Okay, so there are two numbers that we can attach to a given eigenvalue. So there's a fact that's not hard to prove, but we will not really do it. So suppose you have lambda is an eigenvalue of A, then geometric multiplicity of lambda is less than or equal to algebraic multiplicity of lambda. Okay, so this is a fact that's not too hard to prove, but we will not want to prove this in general. Instead, let's now spend some time on examples. In the examples we will work out the eigenvalues and the eigenspaces and the geometric multiplicities, as well as algebraic multiplicities. Okay, let's do that. Let's see. So first example, let's say A is 1, 0, -2, 1, 3, 1, 1, 3, 1. Okay, so we have to compute the characteristic polynomial in order to find the eigenvalues. No. Okay, so this is the characteristic polynomial, but we have to expand this, right? We might have done this before already, but I don't know where the details were written, so we just do it again. So we expand along the first column like that. The benefit of doing that is, of course, that you're missing, you have one term that's 0. So plus minus plus 1, 1, 3 minus t, 3. Okay, so this is 1 minus t, 3 minus t, 1 minus t minus 3 plus minus 2. This is 3 minus 3 plus t, right? Now let's expand everything. So this is t squared minus t minus 1, t minus 3, t minus 4t. This is plus 3 minus 3. Okay. And this, of course, this 3 gets canceled. You just have a negative 2t minus 2t. This 3 also get canceled. So you just have 1 minus t. Well, t squared minus 4t. That's what is it? It's t minus 4t and minus 2t. And of course, doing this tells you that you can factor out the t. Now you just have 1 minus t, t minus 4 minus 2. And that's, well, t, that's, what is it? T minus 4 minus t squared plus 4t minus 2. So that's t minus t squared 5 plus 5t minus 6. So there's an overall negative, but then after that it's t minus 2, t minus 3. Okay, we definitely have done this before, but it's good that we can do it again. So the eigen values are 0, 2, and 3. Now for 0, or for lambda equals to 0, we have to solve this system, ax equals to 0, right? Because lambda is 0. The system is, well, the system to solve is the, 1, 0, minus 2, 1, 3, 1, 1, 3, 1. So I'm just writing the augmented matrix, which we need to process, right? Now what do? We take R3 plus 2 R1 to get rid of the negative 2 there. 0, 3, 3. So 2 R1, right? Minus 2 plus 2 is 0. 1 plus 2 is 3, and 3. Good. Now you see that the row 2 and row 3 are just equal. So R3 minus R2 will give you 1, 1, 1, 0, 3, 3, 0, 0, 0, 0, 0, 0 here. Yeah, like that. Then you continue. I guess if we divide the second row R2 by 3, we get 0, 1, 1 for the second row. Now if we take R1 minus 2, R2, we get 1, 0, 0 for R1, or 0, 0, 1, 1, 0, 0, 0, 0, 0. So the third row doesn't matter anymore. Now we can write out the system that gives us that's given by the first two rows. X1 is 0, that's the first equation. X2 plus X3 is 0, so that means X1 is 0, X2 is negative X3, X3 is still X3. So the vector X, which is X1, X2, X3, is 0, minus X3, X3. So X3 times 0, minus 1, 1. So these are all the possible eigen vectors, right? They are all multiples of the vector 0, minus 1, 1. So the eigenspace is the span of this vector 0, minus 1, 1, and the geometric multiplicity is 1 in this case, which is the same as the algebraic multiplicity for 0, right? Because 0 occurs as only once as a root of the characteristic polynomial. So this is also equal to the algebraic multiplicity. Okay, so that's what happens when lambda is 0. Now when lambda is 2, we want the system AX equals to 2x, i.e. what? A minus twice the identity, x is 0, i.e. now we can write the augmented matrix. 1 minus 2 is negative 1, 0, negative 2, 1, 3 minus 2 is 1, is 1, 1, 3, 1 minus 2, negative 1. Oops, no. Okay. Yeah. Okay, let's see here. Yeah, I need that. 0, 0, 0. Okay, so this is the augmented matrix of the system we need to deal with. Simple enough. Let's process this again. First of all, may want to flip the sign, but let's say R3 minus 2R1, then minus R1. So minus R1 will be make it 1 minus 1 minus 1, 0, 0, 1, 3, 0. R3 minus 2R1 is minus 2 minus 2, so 0. 1 minus 2 is minus 1. Minus 1 minus 2 minus 3, 0. Now you see that the third row and the second row differs by a sign. So R3 plus R2 would cancel R3. Also R1 plus R2 would get rid of the minus 1 in the second entry in the first row. So let's see. Oops. R2 still is 0, 1, 3, 0. R3 becomes the entire 0 row. R1 is 1, 0, 2, 0. Okay. So this is now in reduced row echelon form, which means we can now write equations. Oops, that's not that. Need 2x3 equals 0, x2 plus 3x3 equal to 0. So that is easy to solve. X1 is minus 2x3. X2 is minus 3x3. X3 is still x3. So the vector x, x1, x2, x3 is minus 2x3 minus 3x3, x3, which is x3 times minus 2, minus 3, and 1. So we found all the eigen vectors which tells us that the eigenspace is the span of this vector -2, -3, 1. And again, it's one-dimensional. Geometric multiplicity is 1. Again, the same as the algebraic multiplicity, which is also 1. Okay, that's lambda equals to 2. Now finally, lambda equals to 3. We need to solve the system AX equal to 3x. That's the same, of course, as A minus 3i, x equals to 0. And the augmented matrix is -2, 0, -2, 1, 0, 1, 1, 3, -2. Yeah. Okay. Equal, well, the last column is, of course, 0, 0, 0. And we should proceed to do one thing. Well, in fact, we don't really need to do a lot, right? Without doing any row operations, we already see that the second equation tells you x2, so x3 is 0. The first equation is saying minus x2, x1 plus x2 plus x3 is 0. It doesn't really matter what the third equation says, because x3 being 0 turns the first equation into minus x2, x1 plus x2 equals 0, which is just saying that x2 is 2x1. x1 is still x1. x3 is still 0. Okay. So the vector x can now be described. It's x1, 2x1 for x2, and 0 for x3. So this is x1 times the vector 1, 2, 0. These are all the eigenvectors. So the eigenspace is the span of the vector 1, 2, 0. Again, it's one-dimensional. Geometric multiplicity is 1, which is again the same as the algebraic multiplicity. All right, that took a while, but nothing is really difficult. Okay. So, yes. So once again, let's recall the general statement I'm making here. The geometric, for a given eigenvalue, the geometric multiplicity is less than or equal to the algebraic multiplicity. In the example we just did, these two multiplicities are equal. Now let's look at another example. This time, A is a bit easier. Okay, so this is A, and the goal is the same. We want to find eigenvalues, eigenvectors, and determine these multiplicities. So always the first step is to compute the characteristic polynomial, minus t, 1, 1 minus t, 0, 1, 1 minus t. Should be 0 here. Now this determinant is easy to compute because it's an upper triangular matrix, as you can see. So the determinant is the product of the diagonal entry, which are all 1 minus d. So it just 1 minus d raised to the third power. This immediately tells you that the eigenvalue, there's only one eigenvalue, 1. Algebraic multiplicity is 3. Okay, so now we proceed to determine the eigenspace. So we have to study, we'll have to solve the equation ax equal to 1x, i.e. a minus I, x equals to 0. And we can again write out the augmented matrix. Okay, so this is the augmented matrix. Right, but again, you see that you don't really need any work, right? Because the equations are already telling you that x2 is 0, x3 is 0, x1 is still x1. So x, the vector, is just x1 and 0, 0. So it's x1 times the vector 1, 0, 0. Right? These are all the eigenvectors. Now, the eigenspace is therefore the span of this vector 1, 0, 0. Its dimension is 1. The geometric multiplicity is 1 in this case, which is strictly less than 3, the algebraic multiplicity. Okay, fine. That happens. Now, next example. This time A is 1, 0, 0, 1, 1, 0, 0, 0, 1. Okay, so you again need to find the characteristic polynomial. Again, you're looking at you're gonna see that you're looking at a simple example because the determinant you need to compute is that of a upper triangular matrix. So the determinant is simply the product of the diagonal entries. So you get 1 minus d to the third power. And from this, you can immediately read off the eigenvalue. There's only 1. It's just 1. Algebraic multiplicity 3. Okay, very well. So now let's compute the eigenspace. So we still need to study the system ax equal to 1x. And that's the same as a minus I, x equals to 0. The augmented matrix is again equal to, well, not again, is also easy to write. And this is even easier than the previous example because the equation is already telling you that there's only one, well, there's only one constraint, x2 is 0. So that means the vector x is of the form x1, 0, x3. Now this is x1 times 1, 0, 0 plus x3 times 0, 0, 1. And these are all the eigenvectors. All right. And the eigenspace can now be described is the span of these two vectors, 1, 0, 0, 0, 0, 1. Okay, and it's clear that these two vectors are linearly independent, so the dimension of the eigenspace is 2. Geometric multiplicity is 2, still less than 3. Okay. All right, so now there's a definition to make. Right, given an eigenvalue, we have two multiplicities, the algebraic one and the geometric one. We've claimed that algebraic one is always at least the geometric one. And we've seen examples that the geometric ones can sometimes be strictly less than the algebraic ones. If that happens, the matrix is called defective. So formally, let's say A is an n by n matrix. If there is an eigenvalue lambda of A whose geometric multiplicity is less than its algebraic multiplicity, then A is called defective. Okay, the name certainly suggests that we don't quite like these kind of matrices. They are not as good, and we've seen that defective matrices do happen. So let's just do one more example, maybe. No, maybe not. This is a bit a lot of computations are involved here. Anyway, so what I'm saying is, in summary, when you have an eigenvalue, the dimension of the eigenspace, which is called the geometric multiplicity, can sometimes be less than the algebraic multiplicity, and in that case, the matrix is called defective, and it's not. As the name suggests, it's not a very good situation. So now, now we want to consider the following theorem. Which has something to do with what we can do with eigenvectors. Okay, let's see. So let again, A is an eigenvalue. A is an n by n matrix. A is an n by n matrix. So suppose U1, U2, UK are eigenvectors corresponding to, and this is the point, distinct eigenvalues, lambda 1, lambda 2, up to lambda k. In other words, AUI is lambda I times UI, and lambda I is not equal to lambda J for every I not equal to J. I go from 1 to K, of course. Okay, then now the count here is the content of the theorem. Then this collection of vectors U1 through UK is linearly independent. Okay. Now, let's prove this. Proof. How do we prove this? So first of all, if you just have U1, right? Each eigenvector is not 0. U1 is certainly a linear independent set. Okay. So then you start throwing in U2, U3, and so on. So I mean, it's maybe it's possible that at some point, after throwing in U2 and several more, you get a set that's linearly dependent. So you can suppose the situation is that if you suppose that U1, U2 up to UM minus 1 is linearly independent, but when you add UM, it becomes linearly dependent. Okay. And M is, let's assume that M is less than or equal to K. I suppose this happens at some point when you're doing the process of adding U's. Then what does this mean? Being linearly dependent here means that then there exist scalars C1, C2 to Cm not O0 such that being linearly dependent means you have a linear combination that's equal to 0 with whose coefficients are not O0. Hold on. So right, being linearly dependent means this. So if Cm is 0, then this equation becomes C1U1 plus C2U2 plus Cm minus 1 Um minus 1 equal to 0 with C1 through Cm minus 1 not O0, which means that U1 through Um minus 1 is linearly dependent a contradiction, right? We're assuming that u1 through un minus 1 is linearly independent. If Cm is 0, then we would get that they are linearly dependent. That's not what we assume. So Cm is not 0. Okay, very good. Now apply A to both sides. What are we getting? Get A, apply to C1 U1 plus C2 U2 plus up to Cm minus 1 Un minus 1 Cm Um equal to A applied to 0. And that, of course, is 0. Now the left-hand side is C1 AU1, C2 AU2, Cm minus 1 AUM minus 1, Cm AUM. So this is supposed to equal to 0. And now each of these AU1, AU2, and so on, they are, because the U's are eigenvectors, these guys are lambda 1 U1 and lambda 2 U2, and so on. Cm minus 1, lambda m minus 1 U1, Um minus 1, Cm lambda lambda m um equal to 0. Okay. So what? Now for the sake of discussion, I should label this equation. This is my equation, and let's label it by star. And of course, what I just did, I apply A to both sides of the equation star, and I get a new equation. This one. Somehow just erase things. C1 lambda 1 U1, C2 lambda 2 U2. I get a new equation like these. Very well. Now multiply star by the following factor, lambda m, gives another equation. Right, star was as you see here, so you just get C1 lambda m U1, C2 lambda m U2, Cm minus 1 lambda m minus 1 plus Cm lambda m equal to 0. You get this equation. Oops. Now taking the difference of the these two equations, we get the following expression: C1 lambda 1 minus lambda m times U1, C2 lambda 2 minus lambda m U2, Cm minus 1 lambda m minus 1 minus lambda m minus 1. And the point is, the last term here are canceled. The right hand side is still 0. Okay. Very good. And now what are we doing? We are assuming, because we've assumed that the eigenvalues are all distinct for these u's, these numbers, these are differences between two eigenvalues. They are not zero. None of them is zero. Okay. Now since this is a linear combination of u1, u2 through um minus 1, which is a linearly independent set. We must have the coefficients all being 0. And as we notice, the factors that are differences between the lambdas, they are not 0. So the c's must be 0. We must have C1, C2 to Cm minus 1 equal to 0. Okay. So what happens? Now, if you take this condition conclusion, see that all the C1 through Cm minus 1 are 0, and go back to star, we just get Cm um equal to 0. Right? Star was this. Because C1 through Cm minus 1 all being 0 means that you just have one term left. Now, because um is an eigenvector, um is not 0. So Cm must then be 0. But this is again a contradiction, because we assume that u1 through um are linearly dependent. So the only way this could have happened is because we made the wrong assumption that u1 through um are linearly dependent. Therefore, in fact, u1 through um are linearly independent for all m less than or equal to k. And that's the theorem. Okay. So what is this theorem telling us? Again, let's go back to the statement. If you have eigenvectors corresponding to distinct eigenvalues, the point being distinct, then these eigenvectors are linearly independent. Okay. And being linearly independent is nice because it's one of the things you need to form a basis. So in particular, you can formulate the following corollary. Again, A is an n by n matrix. Suppose A has n distinct eigenvalues, then A has n linearly independent eigenvectors. Okay. We're being careful here. We're not really calling these n linearly independent eigenvectors a basis because of the issue that we will discuss next, that is, what are these eigenvalues anyway, and eigenvectors? But that's next lecture, and yeah, so let's stop here.